Not sure how I did it, but I ended up ending the previous recording early, so we're going to make this to a separate video, which is probably for the best. Okay, so let's look at water. That way we can find some expressions that we can actually use with this. So let's derive some more equations. So say we have water interacting with water. It's going to break apart into H3O plus and OH minus. We know the pH of water is 7. What that means is that we have 10 to negative 7 for our concentration of hydronium ions. Because it breaks into OH minus at equal concentrations, we also have 10 to the negative 7 of hydroxides as well. Which tells me that the equilibrium constant for water, hence the W, is going to be products of reactants. You don't include liquids, so the reactant side is negligible. And this is going to give me H3O plus times OH minus, and 10 to negative 14. You can probably see this as 1.0 times 10 to negative 14. So this is one of our first very important equations. Next, we can take the sum of some of the equations we had up above. So like Ka times Kb. So Ka was expressed as H3O plus A minus over HA, and Kb was expressed as, now I wrote it as HB, but here just keep the terms the same, HA rather than HB. Instead of putting a B or B minus on the bottom, I'm going to put an A minus, so they match. And here is an OH minus up there. So that would be our base expression, just I had B's in these positions. From here, we can see that many of these terms cancel out. But what I'm left with is H3O plus and OH minus. So this is our next relationship. Ka times Kb is equal to H3O plus times OH minus, which we showed up above is equal to negative 14. So I guess this is actually all the relationships put together. So say we want to do a logarithm now. So now we're going to do the negative log of everything. And we're going to distribute those out, so we're going to resolve it, all that good stuff. So that ends up giving us pKa plus pKb equals pH plus POH equals 14. So here's our next set of relationships. If you know these two we have boxed in blue, we are in very good shape. So let's write this into a chart. So we have H plus, OH minus. So we have pH, we have POH, and I want to convert between everything. For simplicity, I'm only going to write the base equation for these two. H plus times OH minus is 10 negative 14. And here we're going to do pH plus POH equals 14. You can just use a little bit of algebra to solve for those. For these on the side, yeah, you can still use a little bit of algebra to solve for them, but because most people aren't used to doing it, I'm going to write it out. So negative log of the OH is equal to POH. Do the same thing on this side. So the negative log of H plus or H3O plus is pH. And then to go the other direction, we have 10 to the negative POH equals OH. And to go up, we have 10 to the negative pH equals H plus. Cool. We have another version of this chart where everything just gets copied back over, but we just replace the variables. So now we're going to do Ka, Kb, pKa, pKb. So as before, to go between these two, Ka times Kb equals 10 negative 14. Go between these two, pKa plus pKb equals 14. To To go between these, now I'm just going to write it once because I don't really want to. The negative log of KB equals PKB. The negative log of KA is PKA. Cool. So now you have all the relationships found. If they give you Ka, but you need PKB, you have to go around this way or you have to go around this way to get to it. If they give you the concentration of H+, but they're asking for the POH, same thing. You go around. Yes, you can algebraically go right down the middle. If you just substituted in one of these equations into another, that can absolutely be done. But for most people, that's not necessary. And it's probably just quicker to just know this chart and how to sneak through it. A very likely circumstance you'll be in is that you'll be solving for POH or OH, and they're asking for pH. So you'll need to go around some direction to get here. Now the most direct route makes the most sense. So if they give you OH and you're solving for H+, you're going to use this. But you could switch it to POH, switch it to pH, and then go to H+. Total waste of time, but it works and you can do it. But if you're going from one side to the opposite side, this is a very common thing where you'll be using maybe a KB expression, you're dealing with a base, so you're solving for OH-, but it asks you what's the pH of solution. You're going to be solving for OH, but you need pH. Pick a direction. Change it in H+ and do the negative log of it, or do the negative log of it first. You're dealing with like bigger looking numbers that are a little bit easier to put your head around, and then 14 minus that answer rather than a bunch of dividing. It doesn't matter. Get the same answer. It's all fine. So the next question is, how do we relate these two charts to each other? Well, we did that. That was done on the very first page. Very first few pages, not the first page, second page. That's what all this was. That was relating them together. You can see that there's a relationship between pH and pK, but it involves the concentrations of the acids and bases. There's a relationship between H+ and Ka, but it involves the concentration of the acids and bases. And the same thing is true on the base side. So to convert from one chart to the other, you need to incorporate the acids and bases somehow. You need to be able to incorporate the remainder of that chart. And that simply comes from the Henderson-Hasselbalch equation or its non-logarithmic counterpart, which is just the equation for equilibria. And lastly, I did not cover it here, but you can utilize ice tables for solving some of these expressions. Say you have some initial concentration of acid and you have some initial concentration of base. This is technically 10⁻⁷, but for all intents and purposes we just say it's 0 because it's pretty negligible. You're going to have some change in this. You're going to have some gain in this. So we have acid minus X, we have X, we have base plus X. Typically speaking, the Ka value is pretty small. They write it like this. It's pretty small. And when it's very small, then taking a relatively big number and subtracting a tiny number from it doesn't really change anything. This is still approximately what you started with. And this is still approximately what you started with, because you can kind of ignore. So now we end up getting the expression that Ka equals X times base over acid. X is just your equilibrium concentration of H+. So let me write that in, H+. And we already did this expression. In fact, if I was to replace base and acid with its respective terms of A- and HA, we literally have the equation for equilibrium constant. Ka equals H plus times A minus over HA. So the ice table you can absolutely use for these. It's not going to be particularly complicated. But it's always going to turn into you saying Ka equals H plus A minus over HA. And this is what turns into the Henderson-Hasselbalch equation of the pKa equaling the pH minus the log of base over acid. So, that's all cool. When you're dealing with buffers, you tend to use one of these two. Ice table, not entirely necessary, because those values for x tend to be super negligible. So we're going to do a bunch of examples where we're just using these two expressions, because we can. We're going to make it easy.